Calculus, Unit 7, Day 61, Part 3. Given a slope field, sketch a solution curve through a given point. So to the right is picture the slope field that you developed from the differential equation on the previous page. So that was the first one we did, dy dx equals x minus 1. Sketch the solution curve through the point 1, negative 1. So they're specifically asking us to do it through that point. To do this, you find the point and then follow the slopes as you connect the lines. So just remember, as I said before, like, hey, this dy dx is linear, so we know it should look quadratic. It should be, so when I raise it to the 1 power 1 more, under the power rule, it's going to be x squared, so it's going to be quadratic, which means it's going to be a parabola. So let's take a look at this. So let's first find 1, negative 1. And it looks like, hey, I'm going to somehow go through there and go through there. And notice this is asking us to sketch, okay? Sketch the solution curve. It doesn't have to be exact, all right? And maybe it's maybe it was there, maybe it was supposed to go a little bit further over that side, maybe it was supposed to go a little bit wider there, and that's okay. So we're just getting an idea, but then I know there should be an infinite number of these parabolas, okay? But that's the one that goes through this point. Okay, so the third thing they're going to ask us to do is match a slope field to a differential equation. So since the slope field represents all of the particular solutions to a differential equation, and the solution represents the antiderivative of a differential equation, then the slope field should take the shape of the antiderivative of dy dx. Okay, match the slope fields to the differential equations on the next page. So this is kind of a pain in the butt that we have to bounce back and forth. All right, and I think I have these on a couple different pages here. So some of the things I might look for is, hey, I have an x, so I know my original equation is going to be an x squared. And that's really where I should start, is try to start working and going backwards. And same thing, I know this is a linear function, that's going to be a quadratic. This is x squared, so it's going to be a cubic. But then I can go back and start trying to, as I look at these graphs, I can start trying to look like, hey, there's a quadratic right there. I can see all the parabolas right there. One of them looked like it was a upside down parabola. I don't know if I have them all on here. Yeah, there you go. There's my upside down parabola. One was a x to the third, which could look a couple different ways. It looks like this kind of goes up, flattens out, then goes back up. And again, we'll check all these. So let's start going back to those other pages and start doing the um, separating the variables and going through and finding out what the particular equation is. So we know the antiderivative is y equals negative cosine x. Oop, I wrote dx. I meant to write plus c. And so now all I do is go back up above and let's check all these graphs. And I think I can get them all there. And this I is going to be the one. So we know it normally starts, so all the negative part does is it reflects it over the x-axis. Okay? So let's keep taking the antiderivative of these functions and matching them up to one of the graphs. So the second one we're going to get, again, we're doing what we've already done, separation of variables, then take the integral. Oh, I forgot the dx over here. Um, So now we get y equals, that's 2x squared over 2, which is x squared, plus 4x plus the constant. So there's going to be an infinite number of solutions. So let's look back at the graphs. And again, I know it's a parabola that's opening up. Um, hey, this is a parabola open up. Let me just check to see if there's any other. This parabola opens up, but it's at the origin, it looks like. So this one's going to slide over. So, and I could check that with a calculator. Looks like over here we got a parabola that's opening down. This looks like either a sine or a cosine curve. We'll come back to that. No, it looks like it's going to be A. Okay, let's write that down and keep going. So in the third one, again, we multiply both sides by dx. Take the integral of both sides, y equals e to the x plus c. So that is going to end up being an exponential growth. E is just a constant, so that was one that looks like the cube. Um, this This looks like it's a sinusoidal function. Sinusoidal. Um, that looks like it's a parabola. Parabola. This looks like it's almost like a quartic. We already did I. So it looks like it's just going to be B. Okay, so that's the only one. So let's write that down and keep going. So we multiply both sides by dx. Again, this is stuff we did in day 60, and now we're just taking the antiderivative, and we're coming up with a general solution. And I have to recognize what does the graph look like. So some of our basic families of functions. So this is a linear function, it's a line, um, and we're trying to find the general solution of this differential equation. So all this stuff over here is all old material. It's now just connecting it to what we have for the graphs. And the only line, I didn't really look at this one, is L. Everything else has some curves in it. All right, so keep going. What did we say that was? J. All right, and I have these on my next page. Okay, so we've set them all up on this whole page. Take a second to try to solve. Take the antiderivative of each of these, then we'll match them up. So you give it a shot. I'll put the answers in a second. I'll match them up to the graphs, and we'll take a quick look at those. So number 5, add 1, divide by the same constant. So we end up getting a quartic, and that's going to be graph H, and we're going to take a peek at that. So, hey, that looks like they're all tails are going up, come down, up, back down, and then up forever. Okay, so that's our quartic right there. Okay, so number 6 ends up being y equals 2 sine x plus c. So when we look at the graphs, um, we end up here was the other sinusoidal function. Hey, it looks like it starts at 0, which the sine of 0 is 0, and it goes up twice as high. We're not really worried about the height, but so hey, this is going to be our sinusoidal function. Number 7 ends up being 4x minus x squared plus c. Don't get tricked that this is a linear function. Obviously, the highest degree is 2. So it's a quadratic, it's a parabola, but the leading coefficient is negative, so it opens down. So that's going to be G. Okay, parabola and opening down. Number 8 is x squared over 2 plus c. That's a parabola that's opening up. And that is going to be right here. Okay, let's do the last two. So number 9 is going to be x cubed over 3. That's a cubic function. That's going to end up being c. We'll take a look at it in a second. Number 10, remember 1 over x. This is hard, but if we can just remember that anytime if I rewrote it, that'd be x to negative 1, and I take the antiderivative, that'd be x to the 0 over 0. That's our special case for natural log. So this ends up being negative natural log of x, absolute value of x plus c. So let's look at those two graphs. So the first one was our cubic function, which we just said was c. And that's right here. That's our cube. Okay, up and down, back up. So that's it. And then our last one is our linear function, which, excuse me, linear, natural log function, which is the inverse of an exponential function. And part of the key is that in this case, it was our, um, it was the absolute value of x. So that's kind of when it looks symmetric. And it was also negative. So normally our exponential function looks like this. So if we have a graph and we normally take a look at, hey, there's our y equals x. So then when I do the, oop, that's supposed to go, sorry, that's supposed to go past that, and then we'll go past that. So that would be our linear function, linear, twice, natural log function, which now when I look at e, when I reflect that over the x-axis, that's going to look like this. Maybe it goes down like that. And then the other side doesn't exist, but the fact that I take the absolute value of it allows the same thing to be on the other side. So that's why we get both sides of that. Okay? And those are things, we haven't done a lot of graphs of those, but that's something hopefully, too, if we thought as the third question, we could skip it till the end and see what the last choice was. But we should still know what that the natural log function is the inverse of an exponential function, which is the reflection over the line y equals x. Okay, so that's the other way that we will use slope fields. Let's go on to the next video to do the last part.